All right, so today we're going to be starting chapter 14. This is probably one of the most, if not the most important lectures that we're going to have throughout the whole quarter. We're going to be covering periodic motion, mostly simple harmonic motion, which if you're a physics major, and I'm sure if you're an engineering major too, you're going to be seeing over and over and over again, pretty much in like all your classes. So let's get started. Now, as I said, simple harmonic motion pops up all the time, especially in physics. An LC circuit is modeled by the equations we're going to be seeing today. Quantum field theory is all based on simple harmonic oscillators. If you go to grad school for physics, if you take quantum mechanics, you're basically going to be doing exclusively quantum harmonic oscillators. So if you take quantum mechanics, you'll see this all the time. Now, just a few things I want to go over before we get into it. That's frequency, angular frequency, and period. So frequency is just the number of oscillations per second. Sometimes you'll see it called the cycles per second. And it's measured in hertz, and a hertz is just one cycle or one oscillation per second. Then angular frequency is just the frequency times 2 pi. And angular frequency is denoted by omega, the Greek letter omega here. So we just multiply the frequency by 2 pi, and we get the angular frequency. And it's important also to remember that the angular frequency is always measured in radians. So whenever you see angular frequency, always just automatically assume it's radians per second. So this is measured in radians per second. And then the period is just the time it takes to complete one full cycle or one full oscillation. And the period and the frequency are inverses of each other. So the period is 1 over frequency, and the frequency is 1 over period. And then let's just review springs. Since simple harmonic motion is basically just spring motion, we're going to be using this a lot. So remember Hooke's law, where we have the restoring force of the spring is given by negative kx, where k is the spring constant, and x is the displacement from equilibrium. So if we have some spring here, this is its equilibrium position at x equals 0. And then this x just measures how far it's displaced from equilibrium, either to the left or to the right. And then k is the spring constant, as I said. And it's called a restoring force because the spring always wants to restore the block or the particle to its equilibrium position, right? If the block is moving out this way, it wants to push it back here. If it's moving out this way, it wants to push it back here. So that's why it's called a restoring force. So when we have a restoring force like this, where the restoring force is directly proportional to the displacement, we get simple harmonic motion. So a spring exhibits simple harmonic motion, and we can find the acceleration just by rearranging our previous equation. Right, we had F is equal to negative kx. We know that F is equal to ma, so we can just rewrite it like that. And then we can see if we just divide both sides by m, we'll get this equation for the acceleration. So this is like our standard simple harmonic motion equation, which we can write in another form. So remember that acceleration is actually the second derivative of position with respect to time. So we can rewrite that previous equation as this. Now you might not have seen this notation before, but I'm going to show it to you right now. So we had in our previous slide that the acceleration is negative k over m times x. We know that the acceleration, like I said, is the second derivative of position with respect to time. Now in physics, we always write the double derivative with respect to time as a dot. So this here, when we have x double dot, that just means the double derivative with respect to time. So for example, if we wanted to write velocity, we would write it as a single dot. And for acceleration, we write a double dot. So that's just a little shorthand that you use a lot in physics. I'm sure if you look at other resources, you might see this notation. It's very common in physics. I'm not sure if it's as common as in engineering, but in physics we use the dot notation all the time. Now one thing to keep in mind about this dot notation is that it only refers to the time derivative. And the reason that we rewrote the equation from the last slide in this form is so that it's clear that we're dealing with a differential equation. Right? So a differential equation is one where the derivative, or the double derivative in our case, depends on the actual current value of your function. So here we have the second derivative is equal to some constant times the function itself. So this is a linear differential equation, and this is basically like our hallmark simple harmonic motion equation. So anytime we see an equation of this form where you have the double derivative with respect to time is equal to negative of some constant here times the original function, that's your indicator that you're dealing with simple harmonic motion. And we're going to see this exact equation come up in a slightly different form in a few slides. All right, now let's see how simple harmonic motion and circular motion are related, because they're actually very intimately connected and sort of the same thing. So let's take a look at a particle undergoing uniform circular motion. So let's say we have a particle that's just traveling in a circle of radius a, and it has an angular speed omega. Now what I want to do is plot only the x component of the particle's position. So what's the x component? Well, let's say our particle moves up here. So let's say it's now moved up here. So the x component, we've got a triangle here. Got a right angle there, and then we've got some angle theta here. So we can see right away that our x component is going to be this adjacent side here, and the adjacent side gets cosine. So this is just a cosine theta. So our x component of the position is just a times cosine theta. All right, now to see how we can actually get simple harmonic motion out of this, let's plot only the x component of the position. So I drew again the x and y axis, but we're only going to be plotting the x component here. So this is just for clarity. So let's just plot this component here. Now, when the particle starts, right here, obviously that's its x component. Now, as it moves up here, its x component is going to be right there. And then as it moves up here, its x component will be here, and so on and so forth around the whole circle. So you can see it starts here, moves here, and then when the particle gets from here to here, now its x component is here. And then as it starts traveling back this way, the x component moves back this way. So if you plot the x component, or you look only at the x component, it looks like it's just oscillating back and forth between these two endpoints. So it's exhibiting simple harmonic motion. And we're going to show actually in a second that it's the exact same equation that we just saw right here. So in order to do that, we're going to need to find the acceleration. So let's look at the particle when it's at that same spot as before. And we know that in circular, uniform circular motion, the acceleration is directed directly inwards towards the center of that circle, right? So we have the acceleration there, and we want to find the x component again. The x component is going to be sort of like that, and we're going to have another little triangle there. So this here is a sub x. Now, what is the x component? Well, you have to think back to like high school geometry, and you know that the x component of the acceleration and the x-axis are parallel, right? So if these are parallel, that means that this angle and this angle are the same. So this angle is also theta. Now we can very easily find the x component because now we have a triangle up here. We know this angle is theta, and we're looking for the adjacent side. So that's again going to get cosine. So our acceleration, the x component of our acceleration, is the acceleration times cosine theta. But it's negative, right? Because here, our acceleration is pointing in the negative direction. So we're going to get a negative sign there. But we don't actually know what the acceleration is, right? We weren't given a. We were only given the radius, which is capital A, and the angular speed omega. So we need to get this acceleration into terms that we know. So again, we can think back to uniform circular motion, and remember that the acceleration is given by v squared over r. So the acceleration is v squared over the radius, and we know the radius here, but we don't know v. Well, again, we can think back to uniform circular motion, and we can remember, or look up, that v is equal to omega r. So now we have everything that we need. So now all we have to do is just substitute in omega r into here, and we can find the acceleration in terms of things that we know. So the acceleration is just v squared, which is omega squared times the radius squared over the radius, which gives us omega squared times a. So this is the acceleration in terms of things that we know. So let me replace this a with this. And now I have that the x component is negative omega squared times the radius times cosine theta. But we already saw a times cosine theta, right? This was just the x component of the position. So we can see here that the acceleration, which we know is the double derivative of position, is directly proportional to the position. So that means that we have our simple harmonic motion differential equation again. So let me just rewrite that so that it's a little bit clearer. So we had the acceleration, and here I'm only talking about the x component. We said the acceleration was equal to negative omega squared a cosine, which was equal to negative omega squared times the position x. So now we can see here that we have this same differential equation, where we have the double derivative with respect to time is equal to a negative constant times the original function. So we have our simple harmonic motion equation, but instead of k over m, now we actually have omega squared. So now we can equate omega with the square root of k over m by comparing to that first equation of simple harmonic motion that we found. And here I'm calling our angular speed and our angular frequency the same thing because they are the same thing. Both angular speed and angular frequency are measured in radians per second, so that means they're the same thing. So this is a very important relation. This angular frequency is equal to square root of k over m. We're going to see that pop up over and over and over again. All right, so let's do an example now to see how this all works. So we have a spring is mounted on a horizontal frictionless table. So we've got table here, the spring is like this, and then we've got our block here. So the block has a mass of 0.5 kilograms. It's attached to the free end of the spring, and a force of 6 newtons is measured to cause a displacement of 0.03 meters. So that means if we pull out this block and spring by applying a force of 6 newtons, it will move 0.03 meters, or 3 centimeters. And now if the block is pulled 0.02 meters to the right and released from rest, find the spring constant, the angular frequency, and the period. So the first thing we want to do is find the spring constant, right? Because we can't do anything without springs if we don't know the spring constant. So we can use the information they gave us here to find the spring constant, because we know that the force is equal to negative kx. So we can find k by dividing the force by the displacement, and that will give us k. Now it may look like I'm ignoring the negative sign, but this equation is the spring force. That means the spring, if I pull out this spring by applying 6 newtons, that means the spring is exerting 6 newtons back. So this negative sign is because the spring has a force in the negative x direction if I'm applying a force of positive 6 newtons, because the forces have to be equal and opposite. So we can divide, let's see, the force was 6 newtons divided by 0.03 meters, and that gives us 200 newton per meter. All right, so now we have our spring constant. So we found that, so this is equal to k. So let's circle that. So we found our first thing. Now we want to find the angular frequency. So that's omega. And we said omega was square root of k over m. So we just do 200, I'm going to ignore the units for now, 200 divided by 0.5, and we take the square root, and that gives us 20 radians per second. So that is our angular frequency. And now we want to find the frequency. So the frequency, Remember, omega is 2 pi times f, so that means the frequency is omega divided by 2 pi. So the frequency is 20 radians per second divided by 2 pi radians, and that gives us 3.2 hertz. And now for the last part, we have to find the period. So the period will just be 1 over the frequency, which is 1 divided by 3.2, and so that gives us 0.31 seconds is the period. Now it's interesting to note here that we didn't use this information at all. So it told us how far the block was originally pulled out before it was released, and we didn't use that at all when we were finding the angular frequency, the frequency, or the period, right? We didn't plug 0.02 in anywhere. So what that means is that no matter how far you pulled out that spring or how not far you pulled it out, the frequency would be the same. It would oscillate with the exact same frequency no matter where you pulled it out to. Because as you can see here, this doesn't depend on the amplitude, right? It just depends on the spring constant and the mass. So those are the only two things that determine the frequency, the angular frequency, and the period is just the spring constant and the mass, nothing else. All right, now we want to write a more general form for the x component of the position for our harmonic oscillator. So before, we just had that the x component was equal to a times cosine theta. But what if I want to write this as a function of time, and I want to make it valid no matter where on the circle my particle starts? So what if the particle starts actually right here instead of over here? How would I be able to write a more general form for this so that all I need to know is the angular speed and where it started? Well, let's say our t equals 0 was right here. So it started over there. And I want to know, like 10 seconds later, what angle is it going to be at? So what's going to be the x component of the position, and that means I need to know the angle theta. So we can actually use our kinematics equations from uniform circular motion. We had theta f is equal to theta I plus omega t. So now what this tells us is that if I start at some initial theta I, so like this one right here, and I'm moving at some angular speed omega, however many 5, 10 seconds later, this is going to be my new angular position, right? So I can just rewrite this x position as a cosine theta I plus omega t. So this is a more general form, right? Because it means I can start anywhere on the circle. I don't have to start at theta is equal to 0. I could start anywhere I want, and I'm still going to be able to find the x component of the position sometime later. So this is actually our general form for the position of a particle undergoing simple harmonic motion. So we can just rewrite this a little bit differently with some different variables as this. So we have the position as a function of time is equal to the radius of that circle that's tracing out times cosine omega t plus phi. Now phi here is playing the role of this initial angle theta I. So this is our theta initial. So wherever the particle is starting at t equals 0, if it's starting, let's say, on the y-axis, that would make theta I 90 degrees, right? Or pi over 2 radians. And this is called our phase angle. So it's called a phase angle, but you can just think of it as like your initial position, your initial starting position in radians. And now our radius here is called the amplitude. So when we plot out this cosine function, we're going to see that it creates a wave with an amplitude a. So now one very important thing here is that this equation, so it will describe both spring motion, just going back and forth on the x-axis, but it also describes the x component of this circular motion here. And we said that uniform circular motion and simple harmonic motion are very, very closely connected and kind of the same thing. And this is why. It's because when you take the x component of the position of a particle that's undergoing uniform circular motion, the x component of that position is displaying simple harmonic motion. Simple harmonic motion is a 1D projection of circular motion because we take a 2D motion here, right? It's in the x and the y direction, and we can project it down onto one dimension. So that's why they have the same equation for their position in that case. So simple, you can kind of think of simple harmonic motion as the 1D version of circular motion. So that's why they're very closely connected, and they actually had the same equations as we saw, right? Now the amplitude, I just want to go over the amplitude quickly in case in case you haven't seen amplitude before. So if I want to plot, let's say 5 times cosine theta, my graph will look like this, right? Where I have a maximum 5 up here and a minimum 5 down here. And then this distance right here is just called the amplitude, right? So it's just that. So in the case of our spring, the amplitude was the distance it was displaced and then released. And then in the case of our circle, it was the radius of the circle. So those are the amplitudes for those two places. So both the maximum displacement in spring motion and the radius in circular motion end up going right here, and they're just called the amplitude. Now I just want to go over the phase angle a little bit because I know this gives people a lot of problems. So let's just write our, let's say our amplitude is 1, so the radius of our circle is 1, and we've got this here. So let's say the phase angle is 0. So if the phase angle is 0, that means that when I start my circular motion, I'm starting right here on the x-axis, and I'm just going to go around this way in a circle, right? So if I want to plot the position with respect to time, it will just trace out a cosine function. So it will just look like this, right? Where this is like one complete revolution. And remember that cosine of 0 is 1, so my cosine graph just starts up here and it ends back up there. Now, what if my phase angle was pi over 2? So what if it was pi over 2 here? That would mean that I start my rotation or my cycle at 90 degrees, right? So I'm starting here and then I'm rotating around that way to get back to the y-axis. So then that means that when I plot this cosine function now, it's actually shifted over by 90 degrees, right? By pi over 2. So now it looks like this. Oops. So if I wanted to plot the x-coordinate of the position versus time for a particle going in a circle that starts up here and then goes around here, it would actually look like this, right? So it's shifted over a little bit compared to this graph, and it's shifted over by 90 degrees by the phase angle. Now, what if I started with my phase angle at pi? Well, then that means that my cycle, my rotation here, is starting on the negative x-axis, and then I'm going around this way, right? So now if I wanted to plot the x component of the position, it would be shifted by pi compared to the first. So that means it would look like that, right? So now it's shifted by pi compared to that first graph where there was no phase angle. So that's just what the phase angle means. It's just a shift of your cosine graph. It's telling you your starting position. Okay, and then I also want to go over what a radian actually is, because everyone uses radians, but I find no one actually knows what they mean. I know I certainly was never taught what a radian actually is. My teacher just started using it. So a radian is, let's say we have a circle here, and it has some radius here, r. And then let's say I took a length of rope that was the length of a radius, so a length r, and I laid it on the circumference of my circle. So I laid it out like that, and this was a length r as well. So a radian is just how many degrees does this slice take up. So if I drew like that, and then I put a little theta here, this is 1 radian. So this is a radian. Now a radian is equal to like 57 degrees. It's 57 point something. So when you see things that say like 2.5 radians or 1 radian, a radian is not equal to pi. A radian is equal to 57, about 57 degrees. Like I said, I think it's like 57.2 or something like that. So 1 radian is equal to about 57 degrees. And now the reason that we use pi to describe radians is because we know the circumference of a circle. So the circumference of a circle is 2 pi r, right? So that means that there are 2 pi radiuses laid out along the circumference of this circle, right? That means that if I took some lengths of rope that were each length r, I could lay out 2 pi of them, so like a little over 6 of them, along this radius. So that's why you usually see pi go along with radians. It's not because 1 radian is equal to pi. It's just because there are 2 pi radians, or 2 pi radiuses, along the circumference of a circle. So 1 radian is equal to 57 degrees, and if you want to switch between radians and degrees, let's say we had 1 radian, and we want to switch that into degrees, you could do times 180 degrees over pi. And that's because there are pi radiuses laid out over half the circle, right? If I looked at just this top half of the circle, we know that that's length pi. So there are pi radiuses laid out over 180 degrees of our circle, right? I could lay out pi of these little ropes here. So we can see here that our radians cancel, and you multiply this by 180 degrees, and you'll get about, like I said, 57 degrees. So this is also good because now you can like estimate when you see something that says like 2.5 radians or 2 radians, you know that 2 radians is going to be about 120 degrees. Okay, so that's what a radian is. All right, so now let's look at the velocity and acceleration of a particle undergoing simple harmonic motion a little more carefully. So here we have the velocity. Now we can get that because we know the x component of the position is cosine omega t plus phi. And we know that the velocity is just the derivative of position. So we have dx dt is equal to a sine, right? Because the derivative of cosine is negative sine. So we have sine and then a negative omega t plus phi. And then we have times omega, because then we have to take the derivative of what's inside here, right? Remember the chain rule. So here we have our velocity, and it's just written a little bit more neatly right here. Now if we plot this, so let's plot the velocity times the time. So this is a negative sine wave, so it's going to look like that, where this is negative omega a, and up here this is omega a. So now the amplitude of our velocity sine wave is actually omega times the amplitude of the position. So we can see here that the maximum velocity the particle obtains, so our Vmax, we can see is actually omega a, right? That's the highest point that our velocity reaches up here. And we can see that the minimum velocity is right here. The minimum velocity is negative omega a. And now what about the acceleration? Well, we can get the acceleration the same way. We said that the velocity is negative omega a sine omega t plus phi. So that means that the acceleration, we just have to take the derivative again. We're going to get negative omega a. The derivative of sine is cosine. So we're going to have cosine omega t plus phi, and then times omega again for the derivative inside here. So we get an omega squared, So we get an omega squared here times the amplitude times the cosine omega t. Okay, and now if we wanted to plot this, so let's plot the acceleration times the time. This is now a negative cosine graph, so it will look like that. Where down here, we're now at negative omega squared a, and up here at the maximum, we're at positive omega squared a. So that means our maximum acceleration that our particle is going to reach when it's undergoing simple harmonic motion is omega squared times a, and the minimum is negative omega squared times a. All right, now let's do a couple of examples. So our first example, we have a block of mass 680 grams is fastened to a spring with spring constant 65 Newton per meter. So we have our spring here. The block is pulled a distance of 11 centimeters from its equilibrium position and then released from rest at t is equal to 0, and we're ignoring friction. What is the maximum speed of the block, and where is the block located when it has that speed? And then what is the maximum acceleration, and where does this occur? So there are a few things we can solve for right away. Right away we know the amplitude, right? Because they tell us that it's pulled 11 centimeters. So right away we know that the amplitude is 11 centimeters. Sorry, then meters. And we can also find the angular frequency right away because they give us k and they give us m. So let's find the angular frequency. So this is going to be 65 divided by 0.680 kilograms because we want everything in standard units. So this is going to give us 9.8. So this is 9.8 radians per second. So now we can find the maximum speed and the maximum acceleration. So notice they're saying maximum speed, so we just have to worry about the magnitude of the velocity. So the maximum speed, as we just saw, will be omega times the amplitude. So Vmax is omega times the amplitude. So we do just 9.8 times 0.11, and that gives us 1.1 meters per second. So I'm being a little bit sloppy with significant figures. Just as a side note, I don't really care about significant figures. So on an exam, you know, use 2 or 3 decimal places. That's fine. I really don't care about significant figures. You know, so this is sufficient. Okay, now we want to know where is the block located when it has this speed. So where is the block when it has its maximum speed? Well, you have to think back to your unit on springs. So when the block is at either of its extreme positions, so when it's pulled either all the way out or it's compressed all the way, its speed is 0, right? Because it comes all the way out, it stops for a second, and then it goes back. So at the extreme positions, the speed is 0. So clearly that's not where our maximum velocity is. So the maximum velocity is actually right when it's passing its midpoint, right? Because it starts from 0 at its extreme point, it starts speeding up, reaches its maximum position in the middle here, and then starts slowing down back to 0 to its maximum compression, and then it just keeps doing that. So you can also do this using conservation of energy. You can show this, which we'll see next. But the maximum speed occurs right when it's passing by that equilibrium point. So this occurs at x is equal to 0. And now we want to know the maximum acceleration. So A max, as we saw in our previous slide, is omega squared A. So we just have to plug in 9.8 squared times 0.11, and that gives us 11 meters per second squared. And now the maximum acceleration occurs at the endpoints, right? Because let me go back to so we can look at our previous slide here when we had the equation for the acceleration. So this is telling us that our acceleration, if we plug in 0 here, so at the point, the equilibrium point where x is equal to 0, our acceleration is just going to be 0, right? So the place where the acceleration is going to be the largest, where the magnitude will be the largest, is when x is the largest, right? Since omega is not changing. So that means that the acceleration is going to be maximum at the endpoints, the magnitude of the acceleration anyway. So we can just write that in here, where our maximum acceleration will occur, the magnitude will occur at the endpoints. So at maximum stretch for the spring or maximum compression. Okay, and now we want to know what is the phase angle for this motion and what is the displacement function x of t for the block. So the phase angle here, we have to look back at what our problem said. So it says that at t is equal to 0, it's pulled a distance of 11 centimeters, so that's its amplitude is at 11 centimeters, and then released. So this actually has a perfect, just regular cosine function. So that means that our phase angle is 0, right? Because it's starting at its maximum amplitude, so it's not offset by any initial theta. Another way to figure that out is we can write here, we know the amplitude is 0.11. We know the position at t equals 0, right? So at 0, we have cosine of omega times 0, so that's 0. So we just have cosine of phi. And we know that at t is equal to 0, the position was that 11 centimeters, right? It was at its maximum amplitude. It was at its maximum position. So we have here 0.11 equals 0.11 times cosine phi. So we can see here that cosine phi has to be equal to 1, right? And that happens when phi is 0. So now what is our displacement function x of t? Well, x of t is equal to the amplitude, which is 0.11, times cosine omega we said was 0.98, 9.8, sorry. 9.8 times t, and then no phase angle. So this is our displacement function here. All right, so let's do one more example. So here at t equals 0, the displacement of a block undergoing simple harmonic motion is negative 8.50 centimeters. The block's velocity at that time is negative 0.920 meters per second, and its acceleration is 47 meters per second. Find the angular frequency of the system, the phase constant, and the amplitude. So here, basically what's happening is we have this is our equilibrium position, and they're telling us that t is equal to 0, the particle is over here at negative 8.5 centimeters. So this is t equals 0. The velocity is directed to the negative side, so it's still moving to the left. And the acceleration is 47 meters per second squared. Okay, so we know it hasn't reached its maximum position over here yet because its velocity is still pointed in this direction, so it's still moving to the left. So let's write down everything we know at t equals 0. So in the x direction, we know that x of 0 at t equals 0 is negative 8.5. Actually, let's write that in meters. So 0.085 is equal to the amplitude times cosine omega t, but here we're at t equals 0, so that will be, so omega t is 0, and then we just have phi left. And that's all we know for the position. So now let's look at the velocity. So the velocity we have is negative 0.92, and that's equal to omega times the negative omega times sine. And again, omega t is 0, so we just have phi there. And then let's look at the acceleration. So then for the acceleration, we have at t is equal to 0, the acceleration is 47 meters per second squared. And we know the acceleration is going to be negative omega squared times the amplitude times cosine omega t, which is 0, plus the phase constant. All right, so we need to find the angular frequency, the phase constant phi, and the amplitude. So the good thing is that we have 3 equations here and 3 unknowns. The bad thing is that that's going to be a little bit complicated to solve. So one thing to keep in mind here is that I want to avoid getting any inverse functions, and if I kind of dive in and try to solve this immediately, you might end up with some like cosine inverses or sine of cosine inverse, and that's very ugly and you generally want to avoid that. So what I can see here, and this kind of trick pops up a lot in physics, so you should keep this in mind, is that I notice if I divide this function by this function, they both have cosines, so if I divide them, the cosines will cancel out, right? And the amplitudes will cancel out, which will leave me with one equation for omega. So that's what I want to do. So I'm going to divide those two. So I'm just going to add a page here so that we can have a little more room. So I'm going to divide x by a. So x we said was 0.085, acceleration we said was 47, and I'm going to divide those two equations by each other. So then we had a cosine phi, and we had negative omega squared a cosine phi. This was negative here. Okay, so like I said, my cosines cancel, the a's cancel, and now I'm left with just negative 0.085 divided by 47 is equal to 1 over negative omega squared. So actually my negatives cancel. And now I can solve this by just taking the inverses. So I can flip this and get omega squared is equal to 0.085, and then just take the square root of both sides, and you get omega is equal to 23.5 radians per second. Okay, so all I did here was just divide the equation for the position by the equation for the acceleration. And that's a very common problem-solving technique in physics, especially when you have a lot of different, like 3 or 4 different variables you have to solve for, and especially when you have trig functions. So, all right, we've got omega now. So now let's find the phase constant. So here I'm going to try something similar, but I'm going to divide the velocity by the position. So now I want to do 0.92 divided by 0.085, so the left-hand side of those equations. This is negative and negative, so those will end up canceling out and giving me positive. The velocity was negative omega times the amplitude sine of phi, and the position was amplitude times cosine phi. So like I said, these cancel out and give positive. The amplitude here cancels out. We know what omega is now, right? We know omega is 23.5 radians per second. And we want to find phi. So remember that tan is actually equal to sine over cosine. So I can simplify this equation. I have 0.92 over 0.085 is equal to negative omega times tan of phi. So then I have 0.92 divided by negative omega and 0.085, and this is equal to tan of phi. So now I can take the tan inverse of both sides, plug in 23.5 right here, and you're going to get that phi is equal to negative 25 degrees. Now I'm putting it in degrees just so that it's a little bit easier, our next step. Alright, so that's my phase constant. Now let's find the amplitude. So the amplitude we can just plug into the x equation. So we can just say negative 0.085 is equal to the amplitude times cosine of negative 25 degrees, because that was our phase constant. And we'll get that cosine of negative 25 is 0.9. Now, if you go to solve for the amplitude, you're going to get a negative answer for the amplitude, right? Because we have a negative over here. Our cosine came out positive, so that means our amplitude has to be negative, right? And a negative amplitude doesn't really make sense. Our amplitude is always positive, so that means that we did something wrong. And the thing that we did wrong was here when we took the inverse tan. So if you remember, when you do inverse trig functions, there's usually two answers, right? So there's actually another answer here, and you have to be really careful because sometimes your calculator will, or most calculators, will only give you the first answer. And in order to get the second answer, you have to add 180. So what we actually want to do is add 180 to this to get that second answer for this equation. So this gives us 155 for phi. And now let's try plugging in 155 here. So let's see what happens if I plug in 155 degrees. So if you plug in 155 degrees into cosine, then you get negative 0.9. And now this makes sense because when we go to solve for our amplitude is clearly positive now because we have a negative here and a negative here, which leaves our amplitude positive. So when you solve for your amplitude here, divide both sides by negative 0.9, and you will get your amplitude is 9.4 centimeters, or 0.094 meters. Okay, so I know that this problem was very complicated. So the two things to really keep in mind here are those dividing tricks we did, where we divided a whole equation by a whole nother equation to make it easier. Now, obviously, there's other ways you can solve this. I generally don't recommend it because when you start doing sine of inverse, cosine of inverse, whatever, it's almost always, you're going to make a mistake and it's going to end up being wrong. So that's why whenever you see equations like this where you have these trig functions, your first thought should always be to try to divide them by each other, because you'll usually either A, cancel the cosine and the cosine out, or you'll be able to get something simpler like a sine over cosine, which will just give you a tangent, and then you only have to take one inverse trig function. Because if you had a bunch of inverse trig functions and then you got to down here where you had to find the second solution, like who knows where your second solution would have been lost. So it's really important to try to keep things as simple as possible, even though I know this doesn't look simple, but this is the simplest way to do it. And the other thing, obviously, is with this trig function. This is something that's going to basically pop up over and over, so you have to be really, really careful when you're doing inverse trig functions on your calculator. Be aware it will only usually give you the first answer, and you have to make sure that that answer that you plug in actually makes physical sense, because if you plug in your first answer and you get like a negative amplitude, that doesn't make sense, and you know you need to go to that second answer by adding 180. Alright, so I had planned on doing more on this lecture, but I think this is long enough. So we're going to continue this lecture on Thursday. We'll do potential energy, and then we'll finish up chapter 14. So as I said previously, this is probably the most important material we're going to do in this class. So really make sure that you study this lecture in particular and the next section, the potential energy and energy in simple harmonic motion. Okay, so that is it, and I will see you guys next time.